Okay, so we have an international conference here, international people. So the first several slides that I'll be showing you, I'll bring you up to speed on why, how, and what we're doing on this project. I will then talk about groundwater monitoring results, dive into a closer look of liquid manure lagoons that we have here in California too, just like in Alberta. Forage crop fields, and then I'll share some thoughts with you on management practices in general and wrap it up. We'll have to get used to the time delay here. So in California, the Regional Water Quality Control Board regulates waste discharges to surface water and to land. They've done that for many years. Land dischargers have to assess their impacts to first encountered groundwater with monitoring wells. Agriculture was largely exempted from this, operated under a waiver program. Dairies in California, and specifically in the Central Valley, use the manure that's generated on the dairies to fertilize forage fields where they grow crops for feeding their cows. And in 2007, this practice was deemed a waste discharge, and regulatory provisions were made to require monitoring well installations pretty much on every single dairy in the Central Valley, and at that time we had 1,400 of those. The Central Valley Dairy Representative Monitoring Program is an alternative that was designed in response to these regulations. It's an alternative to site-by-site groundwater monitoring at individual dairies. It's organized, led, and financed by the Central Valley Dairy community. We're collecting data on a subset of 42 dairies that are representative of the industry and pertinent site conditions. And ultimately, we're tasked to identify management practices that are protective of groundwater quality. What does that mean? For us in California, it means we have to be meeting the drinking water quality objectives. For nitrate, it is 10 milligrams per liter as nitrogen, and that includes the uppermost zone of first encountered groundwater. So if you have groundwater 3 feet below your crops, 3 feet below the root zone, that's where that objective has to be met. If we find that current practices are not protective of groundwater, then we'll have to come up with improved practices by 2019. We are blessed in the Central Valley that you see on the screen there with a Mediterranean climate that allows us to double or even triple crop. All the black dots that you see going up and down the Central Valley, those are our dairies. The red dots that you see superimposed are the 42 monitor dairies that we have in our program. Annual precipitation is roughly between 200 and 500 milliliters in our millimeters per year in our area. That's not enough to irrigate our crops. We get snow melt from the Sierra Nevada. And by and large, we are on highly mineralized soils that have a very wide textural range all the way from dune sand to heavy clays. Most of the dairies that we have are constructed as so-called freestall dairies. So you look inside of a freestall there, and what you see is a flush lane where most of the manure is being deposited on. That concrete flush lane is being flushed several times a day to remove the solids. It undergoes a solid separation process where fiber is recovered for bedding for the cows where they can lay down. Liquids are flushed into the liquid manure lagoons for temporary storage, and from there it's recycled back to the freestall flush lanes. That water is being supplemented on a daily basis from wash water that comes from the milk parlor. And ultimately, the lagoon water is then field applied to fertilize our crops. This shows you pictures of our monitoring wells. We're homing in on 3 different management units on these farms. The first one in the bottom right corner is animal housing, which includes exercise pens or corrals, where the animals spend also a lot of their life. Then in the upper left is one of those manure lagoons. It looks actually really nice in blue, but that's just the reflection of the sky. And then down on the left, the largest proportion of dairies are taken up by these forage fields, and there you see a healthy stand of corn. We have, not approximately, we have 443 wells. They're installed either in clusters, like you see there by the lagoon, or the yellow ones, they're actually nested wells, so there's more than one piezometer in each one of these wellheads that you see. We're doing monthly water level readings and quarterly water quality samples, which comes out to be a pretty substantial data set that we're accumulating. Now, this is a very important figure that we've modified from a figure that was published by Harder and et al. In 2002. It's very important that in irrigated agriculture, you understand, and I tell you that we assess cause and effect between management practices and what we see in monitoring wells in the context of a well source area. Because we have so much recharge, there's always a downward vertical gradient in the shallow aquifer zones. And you can look at then, you can calculate roughly a contributing area. So on the left you have the contributing area A that contributes actual flow to that well. Our investigated area, like a forage field, should then be larger than these contributing areas, so that we can say whatever we find in this well is actually attributable to that particular management unit. You can imagine that you can do that okay. It works pretty well in shallow aquifer conditions, very sandy soils, and large management units with a lot of recharge. It becomes much more difficult the smaller your management units becomes and the deeper your groundwater gets. So now I'm finally getting to results. Well, in a nutshell, it's pretty obvious that we see impacts pretty much everywhere. So most of our corrals, we see nitrate levels above our drinking water limit for nitrate. Most of our fields, we see elevated values of nitrate. I want to home in on these lagoons right now because the next few slides are going to be about that. So we have 36 lagoons that we are investigating. Based on groundwater quality, groundwater concentrations alone, only 11 of those were indicative of lagoon seepage. 11 of them, based on groundwater quality, looks like, hey, they're not impacting groundwater quality. But then 11 of them, results were kind of, well, we don't really know. The concentrations don't tell us that there's a clear signal, and in some cases also monitoring wells may have not been installed perfectly downgrading of these lagoons all the time. Also importantly, for the interpretation of those kinds of results, the absence of detectable impacts to groundwater quality does not necessarily provide conclusive evidence for zero seepage or no impact to groundwater quality. So monitoring wells may actually not be the best tool for looking at these impacts. So we did another type of investigation. We looked at 12 of the lagoons where we didn't have clear impacts. We did 53 temporary soil borings around the perimeter, most of them downgrading of the lagoon. This gave us a data set with increased sampling redundancy. Sometimes, well, in all cases, we were able to really home in on the uppermost few inches of the water table, and in some cases, we were able to get closer to lagoon. Lo and behold, what did we find? With that data set, now all of a sudden, 10 of those 12 sites showed groundwater impacts. We found also a wide range of concentrations around individual lagoons and steep concentration decreases, indicating a relatively small lateral movement away from these lagoons. So really, these groundwater concentrations do not support quantitative analysis of lagoon performance, and that was very frustrating to me. If I find a high ammonium concentration in groundwater near a lagoon, that doesn't support a statement of, hey, this lagoon is seeping a lot. If I find a low concentration, this doesn't support a statement of little seepage. We're always limited or relegated to a statement, something along the lines, hey, groundwater concentrations are indicative of lagoon seepage. Concentrations are not informing us on the concentration of the actual seepage, the seepage rate, or the mass loading rate. So let's look at that. Here's a picture of a lagoon. Many of them look like this. They're not very pretty. And I think because they're so prominent figures or features on dairies, you can see them in Google Earth. They're everywhere. A lot of people jump to the conclusions that these lagoons must leak like sieves. So we actually spend some time and money on estimating and measuring the actual whole lagoon seepage rate. So we did that on 17 lagoons. We used a well-described water balance method with a very sensitive instrumentation. Briefly, we had a wide range of lagoons, wide range in terms of age, their depth, and the native materials they were constructed in. I also have to say that most of them do not have construction information. They were put in place at a time when we didn't have regulation. So like in Alberta, it was like grandpa dug a hole. When you plot our data, you see Julian days on the bottom of the x-axis, and then the depth change and evaporation on the y-axis. So the change in storage, or the depth change, is in blue there. The evaporation is the red line, and then the difference is the seepage. You can express that as millimeters per day. And when we do that, this is a weird projector. Thank you. So our median seepage rate was 0.7 millimeters per day. That was much lower than previously expected. Very interestingly, we did not find an indicator variable, so whether the lagoon was 10 or 20 feet deep, or 50 years old, or 10 years old, or constructed on sand or clay, it didn't make a difference. That actually correlates well to the literature because of the effect of the manure in the lagoon itself. It moderates the seepage rates. For comparison, the USDA NRCS design seepage rate is 0.86 millimeters per day, which is actually higher than what we found on these lagoons that were dug by Grandpa before NRCS existed. All I want to tell you here, this is a very old concept that's been in irrigation textbooks 100 years ago. When you increase irrigation efficiency, now we're moving to the field, you will increase the salinity of the leachate. There's nothing we can do about it. That's the way it is. Farmers, dairy farmers that I represent, are scared of that because from a regulatory perspective, they can only regulate based on groundwater quality concentrations right now. So we might be doing a great job by going to more efficient systems, but the regulator will see that as a bad thing. There's another very interesting thing here, because I'm thinking always about, well, how do I interpret data? So when you plug in some numbers here, with the irrigation water concentration, applied water, ET, and the leaching fraction, in this particular example, you get a concentration of 4,000 milligrams per liter in the leachate. If you now have a very small error in your input, 5% error just on your applied water, which I can tell you with absolute certainty, it happens all the time, your leachate concentration all of a sudden is 2,900. So my point here being is, good luck trying to correlate groundwater concentrations to management practices. You will have a fine time arguing over this for years, when in fact all you're doing is discussing noise. Here are some thoughts about management practices. Many people think about them, the way I understand it, as categorical variables. They're absolutely not. There's a lot of gray shades in there. Even easy things like the compaction of a corral, the slope of a corral, the type of manure removal. There's all shades of gray there. You can do a good job, you can do a bad job. Farmers use many management practices at the same time or in sequence to grow crops. They modify them all the time. I have farmers that have literally done something different on the same field for 10 years. I love this concept. Dairy farmers have to do this already. Looking at the applied nitrogen versus the removed nitrogen. I like it because it gives us an opportunity. It's almost like a teaching tool to make farmers more knowledgeable about what they're doing. We're currently being regulated on that already. The current regulations require an application removal of 1.4. My point with this slide is, again, very small input errors and output errors in your measured variables that you have to calculate that give you very large uncertainty. I've got 1 minute left. I made a big mistake last night. I inserted 2 more slides, and I know now that I have no time to talk about them. But I felt like this is so negative and pessimistic. I'm telling you all these things don't work. Well, we're working on it. We're actually doing very detailed measurements on a field scale where we're looking at demonstrating the concept of the application removal ratio that is actually universally applicable, while the actions to achieve improvements may differ from site. And from here on forward, I just say blah, blah to the next slide, and we'll come to my conclusions, and at the same time, I'll open it up for questions already. I'm on time. Thank you.
The way the projector was just to test a little curveball, to say you did. Very well done. One quick question for Till.
Hello, thanks. I just wonder why those ponds are not covered in the bottom with one of these geotextile impervious sheets.
Say that again?
To put in... Okay, that.
Why are we not lining the ponds? Well, I mean, the existing situations that we didn't have regulations that made them do it. So lining the pond, of course, is much more expensive than Grandpa dug a hole. Okay. So that, of course, we're doing more research on that right now. I mean, the fact of the matter is that we actually compared the mass loading rates that emanated from our lagoons to the overall loading rates of on a dairy, specifically the fields, and it turned out that the lagoons only contribute between 2 and 5% on a dairy farm scale.
That was my second question.
Yes.
Why to put so much effort?
Yes.
The problem that
yes.
It's a point pollution instead of the diffuse pollution.
Because the regulators and the public had a lot of interest in lagoons. That was not our choice. It was because the political climate basically made us do it. I'm glad that we did it now. Yeah. I mean, I'm glad we did it because we found things out that really people made assumptions about it. And we felt like we got to investigate this and get to the bottom of this. Yeah, thank you.